Today we'll study probability. Now the first and the fundamental question is, why do we actually study probability? Life is unpredictable and the concepts of probability help us understand the nature of chance and variation in life. If we look at quantum level, we have Heisenberg uncertainty principle and we have developed probabilistic models of atomic structures to understand the nature of basic blocks of creation. And if we come to our day-to-day life, informally, we use probability all the time. In one of the landmark education courses, there was this profound statement, man is a meaning-making machine. So inherently, all the time, we are assessing information and we are predicting outcomes. From guessing the outcome of a cricket match to the probabilistic score in an examination, we do it all the time. Now, probability theory is being used in numerous fields such as meteorology, insurance, healthcare, research, space exploration, game theory, gambling, and many more. The most important practical application of probability is in the field of statistics. We use probability to create real-life models based on binomial distribution, normal distribution, and then we conduct tests on hypothesis. And based on it, we use time series analysis, bivariate analysis, inferential analysis, and experiments. Another area in which probability is used extensively is in understanding risks and relative risks. Probability is commonly used to measure the vulnerability of any particular disease, and that information is used by researchers and government to plan and deliver healthcare services. In space exploration also, risk assessment is done in carrying out an expedition. So whether or not we are aware of it, but probability is pervasive and all-encompassing, and that is the fun of it. Now, heart of probability lies in permutations and combinations. So in order to have a strong grasp at probability, you must understand permutations and combinations well. If you know permutations and combinations, then it is more than half the job done. So if you are new to probability, my recommendation is go back to permutations and combinations, strengthen your concepts, and then come back to study probability. You'll find it much more easier and interesting that way. I do have a compendium video on permutations and combinations. So what I'll do is I'll provide the link to that video in the description below. You can visit that video and come back again for probability. Now we'll begin with certain terms, and the first term is random experiment. So our probability theory begins with a random experiment. A random experiment is an experiment for which all the outcomes are known in advance. But the exact result, it will not be known until the experiment is completed. A very simple example of random experiment is tossing a fair coin. So if we have a fair coin which has a head on one side and tail on one side, if we toss this coin, it will be either head or tail. But unless we finish tossing up the coin, we'll never know whether it is going to be a head or a tail. So such experiment is called as a random experiment. Another very common random experiment is rolling a fair die. Now on a fair die, we have numbers 1, 2, 3 up to 6. And if we roll a die, on the top face, it can be any one of these numbers 1, 2, 3, 4, 5 and 6. So we know all the outcomes, but unless actually we roll this die, we won't be able to know what is the exact outcome in any particular case. So in probability, we'll be dealing with such random experiments. Now the second term that we'll study is outcome and trial. Now, when we conduct a random experiment, we'll get outcomes. So the result of a random experiment is called as an outcome. And when we conduct this random experiment, we call this a trial. So if we toss a fair coin, it's a trial, and whatever result we get is an outcome of that trial. Now, the third important term is sample space. Now, once we conduct a random experiment, we'll get certain outcomes. Now, set of all possible outcomes is called as sample space. So basically, sample space is a set of all possible outcomes. So essentially, it is a set, and we can use set notation to define sample space. So if we toss a coin, we know there are two outcomes, head or tail. We can define the sample space with this set named S, and then it has two elements, H for head and T for tail. Now suppose we toss two coins. Now if we toss two coins, we can have four outcomes. So in this case, the sample space, it will be head head, head tail, tail head, and tail tail. In the same way, if we roll a die, then we can have 1, 2, 3, 4, 5 and 6. And if we roll a pair of dice, then we'll have 6 outcomes for this first die and 6 outcomes for the second die. So overall we'll have 36 outcomes, and we can represent these outcomes as 1, 1, 1, 2, 1, 6, 2, 1, 2, 2, 2, 6, and 6, 1, 6, 2, and 6, 6. Now if this sample space is a finite set, then we can write number of elements in this sample space. Now for the first one, number of elements in sample space is 2. For this one, NS is 4. Here it is 6. And here in this case, it is 36. Now there will be many cases in which sample space will contain lot of outcomes. In that case, it is not possible to represent all those outcomes in a set notation. So there will be very cumbersome and difficult to represent all the elements or all the sample points. So we call each individual element as sample point. Sample points. So in that case, what we'll do is we'll restrict ourselves to number of elements in sample space. Say for example, suppose we have a well shuffled pack of cards. Now there are 52 cards in that, and we have to select 3 cards. Now in this, writing all the possible combinations of 3 cards, it will be very lengthy, cumbersome and unnecessary. So in this case, what we'll simply do is we'll find number of elements in sample space, and which is total number of ways of drawing 3 cards from a set of 52 cards. Now 3 cards from a set of 52 cards can be chosen in 52. See, 3 ways, which is 52, 51, 50 divided by 6, which is 22,100 ways. So I do not wish to write all these 22,100 cases in my sample space. So I'm happy just writing number of elements in sample space. Now if my sample space has very limited outcomes, then one of the way of representing sample space is through a tree diagram. Now suppose we toss a coin. Now if we toss a coin, we know that outcome is either head or a tail. Now suppose we toss this coin twice. Now we know that when we toss this coin first, it'll be head or tail. Now once we have head, if we toss the coin again, on the next toss, we can have head or tail. In the same way, if first trial results in tail, again we'll toss it, we'll get head or tail. Now this first case is HH, this is HT, this is TH, and this is TT. So this is very simple and elementary case of a tree diagram. But these tree diagrams are very important when we study conditional probability, total probability, and Bayes theorem. So we'll be using tree diagrams in a lot of complicated problems. Now once we have conducted a trial of a random experiment and we know all the possible outcomes, then what? Then comes the superstar of probability, and that is an event. So we study entire probability for this, and this is called as an event. An event is basically a subset of sample space. Now, when we are assessing risk or predicting something, we are generally not concerned about all the possible outcomes. Suppose India plays Pakistan, and we know that there are 3 results possible. India wins, India loses, or there is a tie. So these are the all possible outcomes. But what we are more interested in is the probability that India wins, or what is the probability that India does not lose. So this is what we are more concerned with. So when we conduct a random experiment, our area of focus is probability of something happening or something not happening, and that thing is called as an event. So when we toss 2 coins, we know that its sample spaces head head, head tail, tail head, and tail tail, and that's our sample space. And in this NS is 4. Now suppose in this we want to study what is the probability that we get 2 heads. So getting 2 heads is an event. Now basically event, it is a subset. So again it can be written in set notation, and say for this one we'll say this set is denoted by this letter A, and the event is getting 2 heads. Now when we perform this random experiment, this event A, it will occur if we get this result. That means for this event A, the favorable outcome is HH. So for this, number of element in this set A is simply 1. And the same experiment we can define another event, say this event B, which is getting at least 1 head. Now at least 1 head, we'll choose this. This is also included in at least 1, and this is also included in at least 1. So here we'll have 3 cases, HH, HT, and TH. So in this case, number of favorable outcomes or number of favorable sample points in favor of this event B, it is simply 3. And as we have done for sample space, for a lot of cases, we won't be writing these favorable outcomes. We'll just find number of favorable outcomes, or we'll just find number of elements in this event set. Say for example, we'll take this same random experiment, drawing 3 cards from a pack of 52 cards, and we know that number of elements in sample space is 2, 2, 1, 0, 0. Now we want to find a chance that all 3 cards are spade. Now suppose this is some event, say M. Now we need to find number of elements in this event set M. Now we have to choose 3 cards, and these 3 cards, they must be spade. Now in a deck of 52 cards, we have 13 cards which are spade, and from these 13 we have to select 3 cards, and it can be done in 13C 3 ways. Now for the same random experiment, we can define another event, say N, and it is all 3 cards are aces. Now in a deck of cards, we have 4 aces. Out of these 4, we have to select any 3, and it can be done in 4C 3 ways. So typically in a probability question, unless the question is very simple and it is easier to write sample space, we'll just be writing number of elements in events and number of elements in sample space. Now there will be some cases where sample space will have either countably infinite number of points or uncountably number of infinite points. So in such cases, neither we can write its sample space nor we can write number of elements in sample space. Now one very typical example for this is, suppose there are two people, A and B, and they play a simple game of toss. Whoever gets a head first wins. Now A starts the game. What is the sample space? Now this, if A starts the game, then on the first toss, A gets a head and the game ends. Or it could be A doesn't get a head. Now B, on his or her chance, gets a head, game ends. Or it could be A doesn't get a head, B doesn't get a head. Again, in the second chance, A gets head. Or it could be tail, 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 head, tail, 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 head. And this set, it will have infinite elements. So in this case, number of elements is countably infinite. So basically, if we get a head, then game ends. Else, game continues till we get a head. And we know that both these people, for their whole life, they can keep tossing the coin and it may never result in head. So this is one case where writing NS is not possible. Another case is, suppose we have to choose two real numbers, X and Y, from the interval 0 to 1. Now in this case, all the points X, Y, where X and Y belong to 0, 1 are in sample space. Now there is no way of writing all these points. Now this sample space will have infinite numbers of rational and irrational points and their different combinations, and there's no way we can write this sample space. In such cases, we'll use something called as geometrical probability. We can choose X from 0 to 1. We can choose Y from 0 to 1. And all the points X, Y such that they lie in the set 0 to 1 both included, they'll be represented by this area of square. So in this case, this sample space will correspond to this area. So in geometrical probability, we'll be dealing with lengths, areas and volumes. But this is something which we'll study a little later. Now since sample space and event, they're both set, we can represent them using a Venn diagram. So the most common representation of sample space and event is using box and circle Venn diagram, which we commonly use in sets. So this box, this is our sample space S, and all the outcomes within any event, say A, it is represented by this circle. So we're going to represent event and sample space using Venn diagrams. So basically, NS is number of points in this entire set and NA is number of points in this event A. Now once we have studied events, we can now study complement of an event. Now if we have a random experiment whose sample space is S and we have any event A, then complement of this event A, it is denoted by either A dash, or in some books they'll write A to the power C, or they'll write this A bar. And complement of this event is basically the set which is S minus A. That is, it contains all the points of sample space which are not included in A. So if we have this A here, then everything else in the sample space, it is your complement of an event. And that's your A naught, A bar or A dash. And very clearly we can see that number of elements in A plus number of elements in its complement, it should be equal to number of elements in sample space. At times you'll find that in some cases finding number of elements in A is a little complicated, and it may be possible that finding number of elements in its complementary set, it is easy. In such cases, we'll find number of elements in A using its complement and number of elements in sample space. Suppose we have rolled a die, sample spaces 1, 2, 3, 4, 5 and 6, and suppose we define this event A as getting a multiple of 3. So in this set A, we'll have 2 elements, 3 and 6. Now in this case, A complement is not getting a multiple of 3, not getting a multiple of 3. Now here we'll have 1, 2, 4 and 5. So this is how we define complement of an event. Now there is another type of events which are called as mutually exclusive events. Now the events of a random experiment are said to be mutually exclusive events if occurrence of any one of them prevents or eliminates the occurrence of all other events. So if we take a case of 2 events, say A and B, then they are mutually exclusive if occurrence of one prohibits the occurrence of other. Or in simple words, N A intersection B, it must be 0. That is, they cannot occur together. So such events are called as mutually exclusive events. Now we generalize it. We have A1, A2 and AN, then N A1 intersection A2 intersection AN, it must be 0, and all of them, they must be pairwise mutually exclusive also. So that means N A1 intersection A2, it is 0, N A1 intersection A3 is 0, and all possible combinations, which is simply N AI intersection AJ, it must be equal to 0 whenever I is unequal to J. So such events are called as mutually exclusive events. And these events, they can be represented on Venn diagram by non-intersecting circles. So we have all these N events, A1, A2 and AN, and they are mutually exclusive if none of them intersects the other. Say for example, again we'll take this simple case, rolling a die, sample space 1, 2, 3, 4, 5, 6. Now we have this event A, which is getting a multiple of 3. Now getting a multiple of 3 is 3 and 6, and suppose B is getting a divisor of 4. Now divisors of 4 are 1, 2 and 4. So in this case, we have this sample space, then in this event A we have 2 points, 3 and 6. In this event B we have 3 points, 1, 2 and 4, and then we have this point which doesn't lie in either A or B. Now the next set of events is exhaustive events. Now, events of a random experiment, they are said to be exhaustive if occurrence of at least one of them is certain. It simply means that a set of events, say A1, A2 and AN, they are said to be exhaustive events if they include all the possible outcomes of a sample space. That means N, A1 union A2 union AN, it must be equal to NS. So all these events, A1, A2 and AN, they cover the entire sample space. So when we conduct a trial, then at least one of them, it must occur. Now basically we can represent them in the Venn diagram. This is sample space. Now we have to define N sets such that they cover the entire sample space. Now we can no longer use circle because we have to cover this entire area. So it will be, suppose, this one set and then this second set, third set, fourth set, fifth set, all the sets. So this is, suppose, A1, A2, A3 and AN. So together A1, A2, A3 up to AN, their union, it covers this entire sample space. And such events are called as exhaustive events. Now again, coming back to our example, suppose we roll a die, sample space is 1, 2, 3, 4, 5, 6. Suppose this event A is getting a divisor of 6. Now divisor of 6, they are 1, 2, 3 and 6. B is getting an odd number. So it has 1, 3, 5. And this event C is getting a perfect square. So in this case, we'll have 1 and 4. Now, if we take A union B union C, so it has 1, 2, 3, 4, 5 and 6, all the elements. 1, 2, 3, 4, 5 and 6. So basically, N A union B union C, it is equal to NS, and which in this case is equal to 6. Together, these three events, A, B and C, they are said to be exhaustive. Now, A and B alone, they are not exhaustive because if we take A union B, we have 1, 2, 3, 5 and 6. It doesn't have 4. If we take B union C, it is 1, 3, 4, 5 and A union C is 1, 2, 3, 4 and 6. Neither AB is exhaustive, BC is exhaustive or AC is exhaustive, but together A, B and C, they are exhaustive events. And this question, if I'm going to ask whether A, B, C, they are mutually exclusive, if we look at A intersection B, A intersection B is 3, B intersection C is 1 and A intersection C is 1. So basically, they are not mutually exclusive. So these three events A, B, C, they are exhaustive, but they are not mutually exclusive. Now together with second and third, we can define this fourth one, and this fourth one is mutually exclusive and exhaustive. Now the events A1, A2 and AN, they are said to be mutually exclusive and exhaustive if each pair of events, they have nothing in common. That means AI intersection AJ, it must be phi for all I n equal to j. That means N AI intersection AJ, it should be 0. And also A1 union A2 union AN, it must be equal to sample space. That means NA1 union A2 union AN, it must be equal to NS. Now we represent this Venn diagram. We'll have n partitions which are to cover this entire sample space, and none of them is overlapping. So here we can just define these as these chunks where nothing intersects any other thing. This is A1, A2 and AN. So this is the case of mutually exclusive and exhaustive events. Coming back to the same example, sample spaces 1, 2, 3, 4, 5, 6. Now event A is getting an even number. Now this is 2, 4 and 6, and event B is getting an odd number, and here we have 1, 3 and 5. Now in this case, A intersection B, it is 5, and if we take A union B, it is 1, 2, 3, 4, 5 and 6. It is equal to this sample space. So basically these two events A and B, they are mutually exclusive and exhaustive. Now if we look at A and A naught, then basically we know that A intersection A naught, it is 5, they have nothing in common, and also A union A naught, it is equal to sample space. So basically an event and its complement, they are mutually exclusive and exhaustive. Now the fifth one is equally likely events. Now events of a random experiment, they are said to be equally likely if all the events have same number of elements. Basically for such cases, there is no reason to either prefer or discard any one event. So if events A1, A2 and AN, they are equally likely, then number of elements in A1 must be same as number of elements in A2, and it must be equal to number of elements in AN. So these events are called as equally likely events for a random experiment.